So I'm going to solve one example, or probably I'm going to solve some examples. You are going to solve some examples as well. But before I solve the example, I'm just going to stress the fact that in the strain, the normal component of the strain is the change in the length, and the shear component of the strain is the change in the angle. All right. So just remember, this is a change in the length. This is a change in the angle. Now, it is not a change in the angle, is half the change in the angle. So the change in the angle is twice this number. That's it. So this is a change in the length for a vector in the x1 direction. This is in the x2 direction. This is in the x3 direction. This is a change in the angle between two vectors. One is pointing in the x1 and the other is pointing in the x2. All right, so you are going to see this in these examples. So this is a set of relatively simple examples for you to see how the strain tensor would work. So the examples are relatively simple, but they would help you to see things better. All right, so the first example, we have a displacement field given by these components. So U1 is 0.4 x1, U2 is 0.2 x2, and U3 is equal to 0. And we want to find the strain tensor. So we are looking for the strain tensor. Before we do the strain tensor, I'm just going to plot the old and the new configuration. So you know that basically U1 is basically x1 minus x1. So in order to get x1, you can get x1 by adding U1 to x1 capital. So you can get x1 by adding U1 to x1. So I'm going to use this in order to find the new configuration. So I'm going to start from this configuration. This is all applied to a unit square. And you want to find the new configuration for a unit square. Okay, so basically, I'm going to move the displacement field here. I've got the displacement field U1 is equal to 0.4 x1, and U2 is 0.2 x2, and U3 is basically 0. We have a unit square. This is a unit square. This is x1, this is x2, and we have a unit square over there. Okay, so this is the unit square. And we want to find the new units, or we want to find the unit square in the new configuration after applying this displacement field. So the unit square would be 0, 0, 1, 0, and then you have 1, 1, and then you have 0, 1. So this is the coordinates of the unit square. We want to find this after it has moved. So x1 is basically U1 added to x1, and this is 0.4 x1 added to x1. So this is 1.4 x1. x2 is U2 added to x2. So this is 0.2 x2 added to x2. So this is 1.2 x2. And x3 is basically 0. Since we are working in 2 dimensions, as I said, you don't need to worry about x3. You just cancel out x3. All right, see, x1 small is 1.4 x1. So if you do that, try to draw it here. So if you start from 0, 0, well, you know what? I think it's better if you draw the configuration yourself. I mean, I've solved one example. I want to give you probably 5 minutes to try to draw this yourself. So just like I did in the past, so you have 0, 0. This is x1. This is x2. You are interested in finding x1 small. This is 1.4 x1, so it is 1.4, and x2, if x1 is, x1 is 0, so this will be 0, and then this will be 0 as well. x2 is 1.2, x2, so this is 0 as well. So I know that this point started at 0 and stayed at 0. So I want you to do the same thing and find the new configuration for this unit square, and I want you to draw the new configuration on board so that you can see it. So this is the equation for x1, and this is the equation for x2. Okay, so for the vector, for the point 1, 0, we are going to use again the same equation. So x1 is going to be 1.4, and x2 is going to be 0. So this would move to 1.4 and 0. And then for 1.1, it will move to 1.4, 1.2. And finally, we have 0, 1 will move to 0, 1.2. So this is the new configuration. It's 0, 0, 1.40, 1.42, and 0, 1.2. So if you draw that, you will get it here. So this is the original configuration. It will move into this new configuration. Now, looking into this picture, I want you to imagine if you have a right angle here. So you have the two vectors and the right angle here, and you stretch this square into this larger square, and you think about the right angle. With the right angle would change, and you think about the length in this direction and the length in this direction. How big or small the change is going to be in this direction, and how big and small the change is going to be in this direction. So I want you to have a think about this. If you start from this square, you stretch it into this square, and think about a vector in this direction, if it is going to change length or not, a vector in this direction, if it is going to change length or not, and think about the angle between the two vectors, if it is going to change when you move from here to here. Just think about this square, and think about the square being stretched. Basically, you have a vector in the old square, how the vector is going to look like in the new stretched situation. These two vectors will get longer, and this vector in this direction will be stretched by a factor of 1.2, and this vector in this direction will be stretched by a factor of 1.4. Now the angle is going to be I mean, the angle is right. The angle between the two vectors is a right angle, and it's going to stay like a right angle when we move into the new configuration. Because this is stretching just in this direction and is stretching in this direction. It's not rotating, it's not skewing. So the square is not being skewed at all. So if we assume that this is the case, if we assume that the length is going to change, but the angle is not going to change, what sort of a strain tensor do you expect? So the strain tensor would look like this. Probably just E11, 0, 0, 0, E1, or E22, and 0, 0, 0. And since the third dimension is 0 anyway, I'm just going to put a 0 there. So you'd be expecting having zeros for the off-diagonal terms and numbers on the diagonal terms. Now, we are going to use what we have learned in order to find the strain tensor. And again, then we are going to look into the strain tensor and see if the strain tensor is basically what we expect it to be. Right? See, the strain tensor is basically the gradient of the displacement vector. The displacement vector, is given by these components here. So it is U1 equal to 0.4 x1. U2 is a 0.2 x2, and U3 is a 0. So we find the gradient of the displacement vector, the gradient of U, the derivative of 0.4 x1 with respect to x1, 0.4. All right, probably just write this at least one time, du1 with respect to x1, du1 with respect to x2, du1 with respect to x3, and the same is also true for x2, x2, this is 1, and then du2 with x3, du3, x1, du3, x2, du3 with x3. So this is the displacement gradient tensor. So the derivative of u1 with respect to x1 is 0.4. The derivative of u1 with respect to x2, there is no x2 in there, so it's going to be 0. The derivative of x1 with respect to x3 is a 0 again. If you look into the second component, 0.2 x2 differentiated with respect to x1, this is 0. 0.2 x2 differentiated with respect to x2, this is 0.2. And then you have 0. And if you look into u3, this is 0, 0, and 0. So this is the displacement gradient tensor. In order to find the strain tensor is basically half the gradient of the displacement added to the transpose of the gradient of the displacement. So we have the gradient of the displacement. We need to find the transpose of this. The transpose of this is basically all the rows and columns are switched. So this row would become a column, so 0.400. And then this row would become a column, so it is 0, 0.2, and 0. And the last row would become also a column, so it is 0, 0, and 0. All right, so we have the displacement gradient and we have the transpose of the displacement gradient. We add them together and divide by half. So it is half 0.4, 0, 0, 0, 0.2, and 0, 0, 0, and 0, added to basically the matrix itself. If you look into this matrix, you'll see that this is symmetric, and then the transpose will be equal to the matrix itself. And then the strain tensor is basically going to be 0.4, 0, and 0, 0, 0.2, 0, 0, 0, and 0. So this is the strain tensor. And if you look into what we expected originally is something similar. And the change in the unit length in the direction, I mean, if we start from a vector in this direction and a vector in this direction, the length of this vector is 1 and the length of this vector is 1, then this 1 will stretch into 1.4 and this 1 will stretch into 1.2. So this is the change in the unit length and this is the change in the unit length. All right, so this is because the vector is changing from 1 to 1.4 and this is in the direction of x2, the vector length is changing from 1 to 1.2. So I want you now to solve the second example yourself. First of all, I want you, I mean, this is the displacement vector. U1 is equal to alpha x2 and U2 is equal to 0, U3 is equal to 0. I want you first of all to draw the new configuration. I mean, this is the new configuration, but I want you to try and draw it yourself. And then we are going to discuss what sort of components you expect. And then we are going to find the displacement of the strain tensor. So please, just first of all, try to draw the new configuration. As I said, x1 is equal to x1 added to u1. And you can do the same thing for any component. So it is I if you want. So draw the new configuration first. And then I'm going to ask you, how do you expect the change to happen if you move from here to here? If you look into this new configuration, I mean, first of all, do you think there will be change in the length of a vector pointing in this direction or a vector pointing in this direction? And do you think there will be a change in the angle for a vector for these two vectors? I mean, what do you think? Is there going to be a change in the length? Let us start from the angle itself. I mean, you have a square or you have a right angle here, but then in here, I'm going to assume that this vector is going to stay parallel to the side of the rectangle. And then this is going to probably stay parallel. And the angle would be certainly skewed. So the angle is not going to remain right angle. There will be a change in the angle by a certain amount. In fact, we can exactly tell the amount that the angle has changed by, but there will be a change in the angle. All right, this is correct. Now, how about the length? So the length in x2, this is x2, the length in this direction would be changing. Who would agree with this? Who would disagree with this? So if you look into this square and you try to see this square here, I mean, assuming that this is, I mean, it says, just first of all, just excuse the scale here, but this is meant to be 1. Oops. Meant to be 1 here. Because, see, the x2 is 1, so this is the 1 coordinate. And if you look into the original length, so the original length would cover the space from this point to this point. Oops. So this is the original length, and this is the new length. So if you think about it, this length here must be longer than this length here. So there should be some stretch in this length. This is in principle. But because we are dealing with infinitely small strains, so these deformations are extremely small, we assume that the angle here is very, very, very small. I'm talking about probably 10 to the power minus 7 or 10 to the power minus 3 or 10 to the power minus 5 radians. So because that this is a very small angle, we make the assumption that this length is equal to this length. Now, this is quite critical because it's a major assumption. If you try to be accurate or very accurate, then the length would change. But because we are working with very small angles and very small deformations, then we can still assume that the length would not change. And if you look into the name of this tensor, find that the name of this tensor is infinitesimal strain tensor. Now we call it infinitesimal because it's going to describe the strain only when the strains are extremely small. If the strains are large, then this strain tensor would not describe anything accurately. It works just because we are working with extremely small displacements. So in this case, you are making the assumption that alpha is extremely small. But if you take alpha to be large, if alpha is 1 radian, for example, then this is completely rubbish calculations. But because we are dealing with infinitely small strains, because alpha is extremely small, then in this case, we can assume that this length would not change. All right? Now, the length would not change, but just like Alexandros noted right from the beginning, the angle would change. So in this case, the angle would change, but the length would not change. All right. See, if the angle is going to change and the length is not going to change, then the strain tensor, oops, just draw it here. So this 0, some number, and then 0 because everything happening in the third dimension is 0, and then we have e to 1, and then 0, and 0, 0, 0, 0. So this is how you expect the strain tensor to look like. It's only component in the shear because it's only change in the angle, but the diagonal terms, the normal strains are going to be equal to 0. And of course, everything happening in the third dimension is equal to 0. So now I want you to find the strain tensor. Basically, find the displacement gradient vector, the transpose of the displacement gradient vector, and the strain tensor. Just use I just use these components. I will move them here. So U1 is equal to alpha x 2, u2 is equal to 0, and u3 is equal to 0. So first of all, you find the derivative of u1 with respect to x1, and then x2, and then x3. u1 is a function of x2 only, so the derivative with respect to x1 is 0, with respect to x2 is alpha, with respect to x3 is 0. u2 is 0, so the derivative of that is going to certainly be 0, and u3 is 0, so the derivative will also be 0. The transpose of this is going to be just, you switch this row into a column, so it is 0, alpha, 0, and then this row would become a column, and then this row would also become a column. So you need to add this one. This is delta, the gradient of u, and this is the transpose of the gradient of u. So you add both of them and you divide by 2. Adding both of them is going to be alpha divided by 2, alpha divided by 2, and then everything else is 0. So if you look into this strain tensor, you'll see that this is pretty much what we expected from the beginning. So you have zeros everywhere except for the shear components in the 1, 2 direction. All right, now we have a third example. In the third example, we have u1 to be minus alpha x2, and u2 is plus alpha x1. So again, I want you to draw this, and we are going to discuss the change in the length and the change in the angle. I want you now to tell me, what do you think about this? These two vectors, length, or would they change angle, or would they change both if they move from this configuration to this one here? If you look into the change in the change in the length is again negligible, so the length would stay the same. If this is a unit square, it is going to stay as a unit square. And if you look into the angle, these two vectors would rotate at the same time as the box is rotating, but they would still be parallel. Sorry, this is a mistake. So this would still be parallel to the edges of the square. See, if the angle of if the corner angle of the square would stay as a right angle, then these squares, or the angle between the vectors would also remain as a right angle. So this vector would be parallel to this side, and this vector would remain parallel to this side. And since these two sides are basically right angles, then the angle here would still be right angle. So what is happening here is just that the entire square is rotating by an alpha angle. So it's just a rotation by an angle alpha, and the entire square would remain to be the same. Now, how about this type of strain tensor? What do you expect the strain tensor to look like now? So the displacement and the strain tensor should be basically zeros everywhere. So I just probably put it here, 0, 0, 0, 0, 0, 0. So it is zeros everywhere, and the components are in minus alpha x2 u2 is alpha x1, and u3 is equal to 0. So calculate the strain tensor, just find the displacement gradients and the transpose of that, add them together, and then the strain tensor should be zeros everywhere. As I said, the strain tensor is going to be zeros everywhere. All right, so now I'm going to solve an example about the change in the length in a certain direction. So this is the displacement field is given in this expression, and we want to find the strain tensor. So I want you to solve this example and find the strain tensor for this displacement field. Once you have the strain tensor, I'm going to solve the remaining part of this example. So finding the strain tensor is just the same like you have been doing so far. You don't need to draw anything. I want you just to find the strain tensor for this example. U1 is kx2 squared, and u2 is equal to u3 is equal to 0. So I'll just do the full thing now. So u1 is equal to a x2 squared, u2 is equal to u3 is equal to 0. So the displacement gradient tensor is the derivative of this one with respect to x1, this is 0. The derivative of this one with respect to x2, this is 2. Ck is not function of x2, is not a function of x2. And the derivative of x2 squared is 2x2 squared, 2x2. So you just reduce the order of the exponent by 1. And then the derivative with respect to x3 is 0. u2 is 0, so the derivative is 0 everywhere. And this is the gradient of the displacement. The transpose of that is just all the rows and columns are switched. So it is 0, 2k, x2, and 0, and then 0, 0, 0, 0, 0, 0. You add both of them. So this will give you the strain tensor. It is 2. The gradient of the displacement added to the, oops. So the strain tensor is going to be then the displacement gradient added to the transpose of the displacement gradient. So it is basically 2 multiplied by 0. Then you have 2k2x2 added to 0, and then 0 added to 0. Here you have 2x2k2 added to 0, and 0, 0, 0, 0, and 0. Now, sorry, it is divided by 2. So this is half, is not 2. So the half will cancel with these 2's here. So I'm just going to cancel them. And then you have kx2, kx2. This is the strain tensor. All right? So this is the strain tensor. Once you have the strain tensor, the question is to find the change in the unit length for a vector defined by this at point this. So we have a specific point. So we have a specific point. We want to evaluate the strain tensor at, and we want to find a change in the unit length in the direction of E1, and the same for E2. All right, see, we have a unit elongation in the material in the direction of E1 and E2. So just like I said, if you want to find a change in the unit length in a direction of a vector, you multiply the vector. So you have a vector n, you want to find the change in the unit length in the direction of n. The change is going to be n multiplied from left and right. If you have two vectors, n and m, you want to find the change in the length, you can have it as e n multiplied with e multiplied with m, or you switch them back, so it is m multiplied with e multiplied with m. All right, it doesn't make any difference if we multiply it from left or right, n and m. You can switch them because the change in the angle is going to be the same no matter you take it from left or you take it from right. So this is the strain tensor. We want first of all to evaluate the strain tensor at this point 0, 1, 0. So at point at 0, 1, 0, we have x1 is equal to 0, x2 is equal to 1, and x3 is equal to 0. And we feed this back into the strain tensor. So I'm just going to move the strain tensor down. So this is the strain tensor. Wrote the strain tensor without the bracket. So we basically feed this information into the strain tensor. So x1 and x2, they do not exist in the strain tensor. It is only x2. x2 is equal to 1, so I'm just going to replace x2 with 1. So this will make it 0, k, 0, k, 0, 0, 0, 0, and 0. Now the question is to find the unit elongation in the direction of E1 and in the direction of E2. So E1 is basically 0, 1, 0. I'm just putting it as a row instead of writing it as a column just to save space. And E2 is, is 1, 0, 0, and E2 is 0, 1, 0. Again, just writing it as a vector, as a row instead of a column. So this is why I put the T in there. Now we want to find the change in the unit length in the direction of E1. So we multiply the matrix E with E1 from left and E1 from right. So multiplying from left and right, I'm just going to write it down here. So it is 1, 0, 0 multiplied with this big guy here, 0, k, 0, k, 0, 0, and 0, 0, 0. So you multiply this row with this column with this row. So 0 multiplied with 1 is 0, k multiplied with 0 is 0, 0 with 0, this is 0. K multiplied with 1, this is k, added to 0 and 0, and then we have 0 for the last column. Now we multiply this again with 1, 0, 0. So 1 multiplied with 0 is 0, 0 multiplied with k is 0, 0 multiplied with 0 is 0. So this is 0, and the change in the unit length in the E1 direction is basically 0. So there is no change in the unit length in the x1 direction, if you want to put it this way. Now we want to do the same thing for E2. So the question is asking to do this for E1 and E2. So I'll just have to replace this with E2. So this is E2, not E1 now. It is 0, 1, 0, and 1. So multiply this one with 0. So 0 with 0 is 0. K with 1 is K. 0 with 0 is 0. So in the first entry, we have K. It is only K multiplied with 1. K with 0 is 0. 0 with 1 is 0. 0 with 0 is 0. And then finally, we have zeros everywhere. Now we want to multiply this row with this column here. 0 with k is 0, 1 with 0 is 0, 0 with 0 is 0, so everything is 0. And you have the change in the unit length in the E2 direction again to be equal to 0. So there is no change in the unit length in the x2 direction. Now the final thing to do is to find a change in the angle between E1 and E2. So now we need to multiply with E1 from left and E2 from right, or E2 from left and E1 from right. It doesn't make any difference. So I'm just going to use E1 from left and E2 from right. So this is E1, E2, E1, E2. All right, so 0 multiplied with 0 is 0. K multiplied with 0 is 0. 0 multiplied with 0, this is 0. So you have 0 entry in there. Then K multiplied with 1 is K. 0 multiplied with 0 is 0. 0 multiplied with 0 is 0. So you have only K left in there. And for the last column, you have 0. Now you have 0 multiplied with 0 is 0, 1 multiplied with k is k, and 0 multiplied with 0 is 0, so you have k. So the change in the angle is k. So basically, if you look into this matrix, there is no normal strains, and this is why you don't have a change in the unit length in the x1 direction or a change in the unit length in the x2 direction, but you have a change in the angle between x1 and x2, so this is the k, and this is the k here. All right, so this is the solution of this example. I'm probably going to ask you to solve this last example. I'm going to leave it in there, but before we do that, I'm going to tell you just like the strain tensor, just like the stress tensor, in the strain tensor, you also have the principal stresses or the principal strains, so E1, E2, and E3, and they can be found just by solving an eigenvalue problem. So this is just the same thing we have done for the stresses is also correct in this case. And I don't think we have time to solve the example just now, but I'm going to ask you to solve it in your own time. And then when you come back next week, we can just finish solving this example. So I expect you to solve the full example. Just try to solve the full example. And when you come back next week, we're going to discuss what is left of this example. All right? Okay. And just like the maximum shear strain, maximum shear stress, the maximum shear strain in this case is going to be E1 minus E3. And remember that E1, E2, E3 are put in order. So the largest is E1, the smallest is E3, and E2 is in the one in the middle. And the maximum is going to be E1 minus E3. So I will ask you for next week to solve this example. Once you solve it, come back, and then we are going to go through the solution together. And we try to finish the strains next week.